Okay. If we got a current in a conductor, and if we take a delta X or delta L segment of the conductor, my arrows are in each other's way. So let me do my current. And we got a point out here. The current in this segment produces a magnetic field at this point. You take your sample point, and I'm not even gonna label, and you've got your R vector. Then I'll call it delta B at P. That is magnetic field at P produced by current in this delta L segment here. Now the delta L segment is actually, we're going to take this to be a vector. So I delta L product is a vector. I'll put parentheses around it. So I could either put the arrow over the delta L or over the whole thing, because a multiple of delta L is still a vector, right? And it's I delta L plus your book uses R hat. Which is nice and compact, and I have no disagreement with it. And the book will be very happy that I'm not disagreeing with it. We do this cross product. And then we divide by R squared. And I've got my cross product backward. Apparently I don't, but what's going on? Is what I did this. I delta L is in this direction. You cross that with R, and you get a vector up here that's out of the board. But I know that the current by the, never mind. I have my right hand rule wrong with the thing. Okay. Pretty sure I was writing that out correctly, but when I checked it out, something didn't match. Okay, so anyhow, it's oh, in the transition problems, I told you that it was something like I delta L sine theta with the direction, by the right-hand rule, stuff like that. Not sure how much I told you there, but I didn't use a cross product because those problems were written for non-calculus physics, okay? But as you've more or less mastered those problems, we've talked about how they extend into the physics, into the university physics. So we've actually seen this. I've written this out before. But I want to emphasize it now that in chapter 12, that's one of the rules. Okay? There are only two rules. And the other is Ampere's law, which I talked about a couple of weeks ago. So this is Biot-Savart. Ampere's law. Answer these are stronger with no current breaks. By the loop. The integral of the magnetic field dotted with dl, closed integral around the whole loop, is zero. There could be a magnetic field here. You could have a magnet outside of here, okay? And hold a magnet out here, and there'll be a magnetic field at every point of the loop. I hold the magnet here, and then you have a magnetic field at every point of the loop, okay? But when you integrate around the whole loop, positive contributions and the negative contributions cancel each other out. Okay, so if my magnetic field was in this direction, just a uniform magnetic field in the horizontal direction in the plane of the board, then the parts of the loop that are moving toward the magnetic field are exactly canceled by the parts that are moving away from the magnetic or in the direction of the magnetic field, okay? In other words, as I go around this loop, I do as much left as I do right. I make a whole circuit around the loop. That should be pretty obvious. And also you can connect that with what you learned in multivariable calculus, the integral theorems and so forth. Okay? That's not required because that's not a prerequisite for the course. But since you already know it, to your benefit, try to relate it. You'll learn this more easily and you'll reinforce some very important multivariable calculus. Okay. So I mentioned that and just recommendation. If I want to use them. I want to make sure. I don't remember which way the book notates it. Might be 4 pi epsilon naught. I mean, okay. Okay, your book uses mu naught. Four pi times k prime. So I'll use mu naught. Which turns out to be 4 pi k prime I. Okay. Where I is a total current. If you have a bunch of currents, you could say, well, this would be the sum of it. You can use a summation here if you want to, but we just, I define it to be the total current, so I is a sum of all currents pass through it. Now that could be electron beams that pass through here. It could be ions, or it could be wires carrying currents. And you can think of the Helmholtz coils. You got ballpark 50 loops of current, and you run a current through here, okay? Then each loop is cut by that current. So each loop contributes this much to the integral of the magnetic field around the loop. If you divide that by the length of the loop, say that the current is through the center of the loop, okay? Then you get a uniform magnetic field around those loops. All right, just one example of something you've had your hands on. If we want the current, the magnetic field due to a segment of wire, so let's say here's the x-axis, and here's our wire. Okay, here's where x equals A, here's where x equals B. And here's our point P. Don't want to get too general, so I'm just going to put point P above the center of the wire. So that should be A plus B over 2. Then your typical increment sample point at x equals x asterisk is going to contribute to the magnetic field at this point. So what is the expression delta B? Now, again, we're going to write it in here. We're going to assume the current I in the wire. So delta B is I delta L times R over R hat, etc. So the only thing we need to get the expression for our delta B is the R vector. So what is the R vector? What are the components of the R vector? Okay. Since we're going to get this picture for the delta B, we need an I delta L. We've got I, we've got our delta L. All we need is the R vector. So if I pin people down on the R vector, where does it start? Where does it end? I'm hearing stuff about sines and cosines and Dungeons and Dragons and all kinds of stuff. All right. And what I really want to hear and what I finally dragged out of everybody is, well, it's going to start somewhere in the segment, wherever X star is, which could be anywhere in the increment, and it's going to end at P. So now we can draw our R vector. We can draw it. What are the components of the R vector? Okay. I wanted to pin everybody down on this, and I heard all kinds of stuff again, including cosines. I didn't hear any Dungeons or Dragons, but I'm sure they were lurking there somewhere. But we have everything we need here to say, well, first of all, you know where R goes. You want to say R cosine theta, you know it's from here to here. And we have an X coordinate here, and we have an X coordinate here. X equals X star. That's a sample point, right? I didn't label that on here, but I wrote it down. So presumably you would understand, right? Now, of course, you can make your own diagram and label it as completely as you like. And I could have done a vertical line here and said that's where X equals X star. But things are getting cluttered up enough, so I didn't. And I thought it'd be pretty obvious. So the X component of R is A plus B over 2 minus X star, right? Now, if this is the XY plane, let's just assume it's in the XY plane. There's your R vector. So now you can write out delta B. Leave myself a little more room and write a better delta B. I don't want to write I delta L with an arrow over it. I want to write I delta L times a unit vector in the direction of I delta. What would that unit vector be? Well, we're in this direction, so it'd be the I vector, right? And we cross that with so there's our R vector. Now, I'm dividing the R vector by the magnitude of R, right? I need to do that because this has to be a unit vector. It's an inverse square law, okay? But the magnitude of R I could write as just R without an arrow over the top of, yeah, without an arrow over the top of it. So, this R here can kind of become an R cubed down here, okay? Or we can combine this R in the denominator here with the R in this denominator. And we can say that's over R cubed. So that's going to be over the quantity to the 3/2. This alone would be R squared. The square root of this thing would be our magnitude of R. That would officially go under this to make this a unit vector, but we might as well just put it in the denominator. Okay, so that's going to be I delta L. Well, I cross I is 0, so we don't get anything from this. And I cross J is K. I can just write it this way. That makes sense? Again, I cross I we know to be 0. I cross J is K. So we just do I delta L times D. And now we've got the direction. It's going to be in the K direction. Well, if this is the X direction and this is the Y direction, K is out of the board. And that agrees with the right-hand rule, tells us that if my thumb is here, my fingers surround this wire in the direction of circulation of the magnetic field. And at this point, we'll be at the peak and the magnetic field will be coming out this way. So make sure you reconcile that. And then it's just this over this big ugly denominator, okay? I'm not going to write out the whole integral, and I'm not going to do the integration. But it's just going to be a tangent theta, so, x equals tangent theta or some multiple thereof. So B is the integral A to B of I D heading how to write it over this denominator squared, where I replace x star by x. My delta L is a DL. Actually, delta L could be a dx since we're integrating in the x direction. The delta L is going to be a delta x and we get a dx. Now that stuff. And then I just factor out the k vector, put it over here. I can factor out the I and the D, and ultimately I'm doing the reciprocal of a quadratic term that's quadratic in x. And we just use standard integration technique, integrate that. Okay. Now, usually it's going to be, from 0 to some limit, 0 to L or whatever. But that's how you do the integrals. And usually the integrals will be just a little, the denominators will be a little simpler than that, but it's going to come down to the same thing. You're going to have a quadratic expression to the 3/2 power in your denominator. And you deal with that. Okay. If the wire is infinite, then the integral goes from negative infinity to infinity. Okay. If this isn't in the center of the wire, then there are symmetries you get because this is in the center that make the integral a little nicer. The integral gets a little less nice if you want like a point at the end or a point, just pick a point. P is, okay? P could be out here, be over here, wherever. So your integral is more or less manageable depending where P is, but most manageable if it happens to be on the central axis. Okay? Okay. Now, if you do the integral, of course, your book does give you a formula, and I can't do the integral in my head, and I haven't worked it out. So you're going to get infinite wire. Be something like this. They use a capital R for this distance. I chose to use D. Or instead of 4 pi K prime. There's mu naught. K prime is convenient. Its numerical value is 10 to the negative 7th. If you multiply that by 4 pi, it's 4 pi times 10 to the negative 7th with the appropriate units. We did the solenoid at least a couple of weeks ago when we were using it in the lab and so forth. Again, we can represent the solenoid. Okay, we got a cylinder here. And now we've got a bunch of wires wound around the cylinder. You made one. You take a path this inside the cylinder, and you kind of make a little dot every time one of these wires penetrates the loop. So you imagine this loop is, it goes through the cylinder, and let's say it goes through the cylinder and the plane of the loop contains the axis of the cylinder. Okay, so it's like coming straight down through the center of the cylinder. That way, these currents all come through horizontal. Now that might or might not be important. They penetrate the loop, so that's all that matters. But you want orientations and stuff, and symmetry arguments, you can make them. Okay, so and the thing goes way up here, where there's essentially no magnetic field. Now, what's the magnetic field of this loop? Depends on which way the turns are running. If they're running counterclockwise, then well, I'm not going to get into that. I don't want to make that argument, but you know, if your fingers are in the direction of the loop, your thumb is in the direction of the magnetic field. So each loop gives you a magnetic field. If the current's running counterclockwise, the current's going to be in that direction. Or the magnetic field is going to be in that direction. So let's just assume that, so that you have your magnetic field in here. So then you could have some residual magnetic field along here. You don't get much magnetic field outside of the loop, but you get a little bit of some, unless it's an infinite loop. Because of edge effects and stuff like that. But any magnetic field you get along this path is going to be equal to the magnetic field you get when you move along this path. But moving along this path, you're moving in one direction with respect to the magnetic field. Moving along this path, you're moving in the opposite direction. So your total integral on these sides is going to be zero. Your book has some good pictures. We talked about it earlier. Also, if you're pretty far away here, your magnetic field drops to essentially zero. So that the integral of the magnetic field around this loop is pretty much just the integral along this edge. Okay. So the integral of your B dot dl around the loop turns out to be just the integral and I'm not even going to do a dot product because the magnetic field is parallel to this. Presumably this thing is in the direction of the axis. Okay. That's equal to, okay, now your book does some strange stuff. It is traditionally done where n doesn't necessarily stand for the number of times the current penetrates the loop. It stands for, I think, in many cases, the number of times it penetrates per unit of distance. Okay. Well, I'm going to give this loop a length. Assume it's a rectangular loop, so this distance is equal to this. This would be like the integral from 0 to L of B dx. And that's going to equal mu naught times I, or 4 pi k prime times I. Okay. And that's there's law, right? So to avoid confusion, I don't have room to write it there. And that's my main confusion, okay? Avoid confusion. It's the number of times I penetrates the loop multiplied by I times 4 pi k prime. I'm going to use n sub p for the number of times I penetrates the loop. And if you want to call that mu naught, you can. So it's this. And what does this equal? It's B times L. B is your magnetic field, L is your distance. The integral of the magnetic field from here to here is just equal to the constant magnetic field times the length. You don't have an integration to do. So B equals four pi k prime I times the number of times this thing penetrates divided by the length. Well, this is the number of coils per unit length, right? Number of loops per unit length. And your book uses N for that, not for the number of loops. And that's pretty universally and traditionally done. It's just I find that confuses people a little bit. If I want to talk about this in terms of the number of loops per unit length, okay? So I just want to use Ampere's law says count the number of loops. This development ends up dividing the number of loops by the length. And now I'm going to look, because I don't even remember if they use a lowercase n or a capital N for the number of loops per unit length. So I'm going to cheat and take a look. Okay, so the only thing I didn't know is whether to use capital N or little n here. Okay. Where n is number of penetrations per unit length, or the number of coils per unit length. Because when you wind the solenoid, you're gonna see you're gonna control the number of coils per centimeter or whatever. Okay. Now that's again review, but being a little more precise about some of the terminology and bringing this down to the standard formula. And you note the standard formula has the advantage is it doesn't measure the length of the solenoid. This applies within the solenoid to any point that's not very close to one of the edges, to one of the ends. Okay, at the ends, the symmetry argument kind of breaks down, especially the argument about the integral over this side canceling the integral over this side, okay? And edge effects, well, you can make this thing as long as you like. So you can make the magnetic field out here as close to zero as you like, and so you might as well just assume it's zero. Okay. Now, what about a donut? A torus. Okay, so if you got a torus, I'll just symbolize this by annual ring, and then I'm just going to indicate a bunch of loops around the thing. This just indicates a winding. Okay. This time, the path that I want is just a loop inside the torus. Probably should have drawn that path before I do these loops so you could see that the wires go over the top, but I don't think that's going to be all that visible anyhow. And you can understand it. And that loop is going to have radius going big R or little r. I'm going to choose little r, and I'm just going to take a quick peek at which one they use in the formula. Torus. They use little r. Okay. So I take it back. I don't want to use this loop because the coils never penetrate a loop through the center of the toroid. Okay. So what I want to do is I want to come out here and look at a side view. Just like this. And some small segment of the toroid. Just like what I have up here. Now, the thing that's different between this situation and this situation is the length of this segment here well, I'm sorry, let's say just, okay, we got some length of the segment. So here's L. Your book will have a better picture. And let me redraw the picture. Should have drawn it to show that this thing has an arc. Okay, so here's kind of a blind side view, modified, whatever. Okay, so this is not a plane loop. It's curved so that the top view would just be a segment. Draw the whole thing again. And I should have planned this better. I do apologize, but I'm going to have to like the bullet. But what I'm wanting to look at is some segment of this thing here. This is a top view. And I guess I'll draw the rest of my loops. Okay. This is a top view. This thing is a distance r. Make this picture a little better without destroying the whole thing. So we're looking at a segment of the toroid. And this is down inside the toroid. And you've got your loops. That make any sense? I think that's a better picture. I should have drawn this beforehand. I figured I'd immediately see the best way to draw it, and I overestimated myself. I apologize. Okay, so here it is. Top view, things at distance little r. Bottom view, it's like this. And the arc distance here is L. So now I have a distance L, a constant distance from the center. If I'm going to take a risk and use capital N, because again, I didn't bother to look at the notation. Okay, apologize for that, I should have. But if there are capital N loops around the entire toroid, how many of them cut this loop? Well, I'm going to just tell you that it's just a simple proportion. The circumference of an entire loop around here is 2 pi times its radius. Answer. They're in around the whole loop, or the whole thing. What proportion are in the DL length? It's L over 2 pi r. This length divided by the entire circumference. Does that make sense? Just simple proportion. Assuming n is the total number of loops around the entire toroid. I'm not sure that's how the book defines it, and they do use capital M, but I think that's how they would define it. Okay. So the integral of B dot dl around the entire loop, analogous to what we said here, is just B times L times the total I, where now I isn't the total current penetrating the loop. It's whatever the current is in the wire that's winding around this loop times the number of penetrations. Okay. And this equals, got a good night's sleep last night. There's no good excuse. That's B times L, and that equals the number of penetrations times your current. And then it's times, I'll write mu naught. Now, whether this is correct or not, I'll correct it if it needs to be. But if capital N stands for the number of loops around the entire toroid, this ought to be correct, so that we can solve for N for V. And get mu naught N over 2 pi r times I. And that appears to be exactly what the textbook has. And I conclude that the capital N that the text uses is the only capital N that I could find makes sense of this. Okay, so the authors of the book will be glad to know that I agree. Okay. Seriously, that's the only N that seemed to work. And I should have been aware of that beforehand, but you understand how we reason this out. The point is that this is constant through the toroid, right? It's a constant magnetic field within the solenoid, constant magnetic field within the solenoid, okay? As in this case, it doesn't matter how deep this thing is. in the solenoid, it's still cut by this number of loops, okay? Here, the field depends on how far you are from the center. Because for a given length or given arc length, you cut fewer and fewer loops as you move away from the center, so you get a lesser and lesser magnetic field. Okay? Okay, so those are applications of Ampere's law. So Biot-Savart allows you to calculate fields, and we've calculated fields. We've done the integral for the field of a loop at a point along the axis. You might not remember that. You might not be able to do that if I put it in a quiz right now. And I'm not going to do that. But you'll recognize it when you see it. Okay, so I'll draw some little pictures for some of those situations just to refresh your memory. Okay, here's the magnitude of the field of a long straight wire. The field circulates around the wire according to the right-hand rule. And you can actually do this very easily. You just, here's your wire coming into the board, going out of the board, whichever. And it's penetrating a loop of radius r. So that the length of the loop is 2 pi r, the circumference. So if you're integrating b around this path, now by the Biot-Savart law, b will always be perpendicular to the radial vector, in other words, parallel to a tangent vector around the loop. So that's very easy to see. The magnetic field just goes like this, surrounds like this. Okay. So you multiply B, which is uniform around this loop by symmetry, times the length of that loop, which is the circumference, which is 2 pi r. And again, you get mu naught I or 4 pi k prime I. And that's Ampere's law. Okay. Well, you solve that for B, and this is what you get. Assuming it's an infinite wire. Okay, if it's a finite wire, then you got to go to Biot-Savart and do some integrals. And the integrals can get a little bit challenging. Manageable, but pretty challenging. Okay. If you have two long straight wires, separated by a distance, oh heck, what they're going to use. I just need a symbol, and I want to try to be they're going to use R again. The distance here is R, and that's convenient because this formula is given in terms of R. And how much force is there on this wire due to the electric field from this wire? Okay, I'm going to pull out my standard wire here. Okay, so we got, here's a wire, you know, you're kind of looking on the end of it, and you got a magnetic field surrounding the wire. Okay, let's get closer to the end. Magnetic field surrounding this wire. And you got another wire over here. Okay, so if the current is flowing in, the only direction I can point it is, okay, if it's flowing in this direction, but by my right hand, it's circulating around the wire like this. Okay, so there's another wire over here. What's the direction of the magnetic field that this wire is producing at the position of this wire? Well, it's, yeah, you're doing it. It's going around like this. It'll be going down. Okay. Now, if the current in this second wire, okay, you got a second wire, and you got a magnetic field that's going down and a current in this direction. What's the direction of the force? Okay, imagine a wire here, current, ouch, current, magnetic field surrounding the wire. You got another wire over here, that field is downward. Current in the same direction. So you cross the current with the magnetic field, and you get a force of attraction. Now your book has a good picture of that, but you should be able to do that with your fingers. You know, next time you go by a bunch of power lines, think about the force of attraction, okay? So you got a step I should include. Feel that the second wire would be into the board. If the current's in this direction, the field's surrounding like this, so the field's into the board here, and the current is here. Now I'm just going to do it with my fingers. It's fairly easy to understand. You just reason it out. You got field here, current cross field there. Okay. What's the force? Well, I think your book does this. I was doing it for equal currents, but they don't have to be equal. So I'm going to make this I2. Okay, so what do you get when you cross I2 with B? Well, you got the directions. Yeah, you got the direction. Same thing I did, but okay. How do you get the force? Well, it's just I2 cross B, right? They're perpendicular. So you don't have any sine of theta involved. So you're just gonna get I2 times mu naught, this should be I1 now, I1 over 2 pi r. That's just mu naught I1, I2. 2 pi r.